we're always talking about renewable energy sources, right? But so many of them depend on, whether the sun's out or if the wind's blowing.
Yeah.
But what about something constant?
Yeah.
Something reliable? I mean, under our feet, we've got this huge source of energy.
Oh, yeah. Geothermal.
Geothermal.
Ah,
Tapping into the Earth's heat, it's not exactly a new idea, is it? People have been using it for ages.
no. It's been around for a long time in various forms.
But today we're diving into something a little more cutting edge, a bit more
Deeper. Literally.
deeper, yeah. We're talking about enhanced geothermal systems, or EGS. And we like to go deep on these topics, get to the nitty-gritty of the research. So for this deep dive, we've got a specific study we're going to be focusing on.
Absolutely. And it's a fascinating one. The title is a mouthful, though. From hot rock to useful energy, a global estimate of enhanced geothermal systems potential.
Catchy. We'll just call it this study from now on.
Okay, this study.
So the mission today, just to lay it all out there, is to, pull out the most important bits from this study and see if EGS really could be that energy revolution everyone's talking about.
Exactly. Unpack the potential, look at the numbers, see if it lives up to the hype.
Right. Now, before we get too far, though, let's just back up for a sec, make sure everyone's on the same page. What exactly are we talking about when we say EGS? It's different from the traditional kind of geothermal energy, isn't it?
Yeah, you're right. Traditional geothermal plants, they rely on finding these naturally occurring pockets of hot water or steam underground, basically geothermal hotspots.
Right, geysers and stuff.
Exactly.
Yeah.
And that's great where you have them, but it limits where you can build these plants.
So geographically limited.
Very. And that's what makes EGS so interesting. What this study really digs into is that it could potentially open up geothermal to pretty much anywhere. Instead of relying on those naturally occurring hotspots, you're essentially creating your own deep underground.
So like making your own geyser.
Kind of, yeah. You drill down into hot, dry rock, and then you create these tiny fractures in the rock. Then you pump water down, it circulates through those cracks, heats up from the surrounding rock, and then you bring that hot water back up to generate electricity.
So you're not relying on natural aquifers, you're basically engineering your own geothermal system.
Precisely. And that's what makes it so potentially revolutionary.
Okay, I'm starting to get the picture. Now, this study looked at the potential of EGS globally, right? So what's the big takeaway? What kind of numbers are we talking about here?
Well, this study takes a really comprehensive approach. They looked at different levels of potential: theoretical, technical, economic, and sustainable.
Okay, a lot to unpack there.
Yeah, we'll get into each of those. But one of the key findings, the one that really jumps out, is that they estimated something like 4,600 gigawatts, GWA, of EGS capacity could be built at a cost of 50 euros per megawatt hour, or even less.
Okay, now I'm no energy expert, but 4,600 gigawatts, that sounds like a lot.
It is. To put it in perspective, that's enough to power multiple large continents. It's a seriously significant amount of energy.
Wow. And what about the sustainable side of things? We're talking about renewable energy here, so obviously sustainability is a big deal. What does this study say about that?
You're right, and this study addresses that directly. They estimate that the global sustainable power capacity from EGS could be 256 GWA by 2050.
Okay, so not as high as the, what was it, technical potential?
Right, technical potential is higher, but sustainable potential takes into account the rate at which we can extract heat without depleting the resource over time.
Gotcha, so it's a more,
Conservative.
yeah, conservative estimate, considering the long-term picture. All right, so we've got these big, impressive numbers, but I'm curious, how did the researchers in this study actually figure all this out? What kind of methods did they use to come up with these estimates?
Well, they combined a bunch of different global data sets with some pretty sophisticated modeling techniques. A lot of it revolved around creating these maps showing the temperature at different depths, going down as far as 10 kilometers below the surface.
10 kilometers, that's what, like 6 miles down?
Yeah, pretty deep.
So how do they even measure the temperature that far down?
Well, they used data on the Earth's heat flow. That's the heat escaping from the Earth's interior.
Okay.
They pulled this data from a bunch of sources: the International Heat Flow Commission database, data from the American Association of Petroleum Geologists, and a bunch of regional studies.
So like a global patchwork of heat flow data.
Exactly.
Mm-hmm.
And where they could, they used direct measurements from boreholes, those deep holes drilled into the Earth, to kind of verify their estimates.
So they're cross-referencing to make sure their data is accurate.
Exactly.
But I imagine there are some parts of the world where that kind of detailed heat flow data just isn't available. What did they do about those gaps?
Good question. This study used a method called the similarity method to fill in the blanks. Basically, they looked for areas with similar geological characteristics to the ones where they had good data.
So kind of like if you know how one part of a forest works, you can make some educated guesses about another part of the forest that's similar.
Yeah, that's a good analogy. They used the geological context to make informed estimates.
Okay, that makes sense. So they've got the heat flow data, but there's more to it than just that, right? What about the properties of the rocks themselves?
You're right, the type of rock makes a big difference. Different rocks conduct heat differently.
Oh, right.
To account for this, they used a high-resolution global map called GLM, which shows the different types of rocks present at the surface.
So are they assuming those same rock types extend all the way down 10 kilometers?
To simplify things, yeah. They used average values for different rock types, like granite, sandstone, and things like that.
Okay, so they're saying, all right, this area is mostly granite, so we'll use the average thermal conductivity for granite. Makes sense. But what about heat coming from inside the Earth? Doesn't that play a role too?
Absolutely. This study also considered something called radiogenic heat production, which is the heat generated by radioactive decay within the Earth's crust.
So it's like the Earth has its own internal heater.
Exactly. They estimated average values for different countries to account for this internal heat source. And for their baseline surface temperature, they used NASA data from 2005.
Okay, so lots of different data sources coming together here. What kind of software did they use to manage all of this? It sounds pretty complex.
For the geographical data, they used a program called QGIS. And for all the heavy-duty calculations and simulations, they used MATLAB.
So they're bringing in the big guns.
Yeah, this is a pretty comprehensive global study, so they needed some powerful tools.
Okay, so walk me through their process. How did they actually turn all this data into estimates of potential?
All right, so there were several key steps. First, they built those temperature at depth maps we talked about, combining all those different data sources. Then they calculated the total amount of heat available at different depths.
Okay, so that's like the raw energy potential, right?
Exactly.
Right.
Then they took into account all those real-world limitations, the things that would make it difficult or impossible to actually extract that heat.
Like protected areas, cities, stuff like that.
Right. That gave them the technical potential, which is still pretty substantial, but, more realistic than the theoretical maximum. And then finally, they factored in the economics.
Ah, right. Because it doesn't matter how much energy is there if it costs a fortune to get to it.
Exactly. They look at the levelized cost of electricity, LCOE, which basically tells you the average cost of producing electricity from a particular source over its lifetime.
Okay.
They took into account all the costs, drilling, building the power plant, maintaining it, everything. And then they compared that to the amount of electricity they could realistically expect to generate.
So they're looking for the sweet spot where you get the most bang for your buck, energy-wise.
Precisely. And that gave them the optimal economic potential.
All right, so let's dig into those different types of potential a bit more. Starting with the theoretical potential, what exactly are we talking about there?
So theoretical potential is kind of the upper limit. It's the total amount of heat energy stored in the rock down to 10 kilometers deep that could, in theory, be extracted.
But like in reality, you can't actually extract all of that, right?
No, not with current technology at least. But it gives you a sense of the overall resource base. They calculated this using a specific formula, which takes into account the temperature at different depths, the density of the rock, and its heat capacity.
Okay, lots of variables there. And what about the depth? What depth are we talking about when we consider this theoretical potential?
This study found that most of the heat is found between 6 and 10 kilometers deep, with temperatures in that range typically between 150 and 300 degrees Celsius.
All right, so that's the heat. But we want electricity. How do we get from point A to point B?
Good question. To convert that heat into electricity, they used another formula, which takes into account things like the efficiency of geothermal power plants, their expected lifespan, and something called the capacity factor, which is basically how much of the time a power plant is actually generating electricity.
Right, because a power plant isn't running at full capacity all the time.
Right.
Okay, so we've got the theoretical potential. Now, what about the technical potential? How much of that theoretical energy can we actually get our hands on, realistically?
Well, that's where those real-world limitations come in. Remember, we talked about protected areas, cities, things like that.
Yeah.
Those factors significantly reduce the amount of energy we can practically access. They also factored in things like temperature drawdown, which is how much the rock cools down as you extract heat, and the recovery factor, which is how much of the heat you can actually recover with current technology.
Okay, so like diminishing returns, kind of.
Yeah, you could say that.
So even with those limitations, they still came up with a pretty big number for the technical potential, right?
Right. Still significant, but significantly less than the theoretical potential.
Makes sense. Now let's talk money. What about the economic potential? How much of this energy can we afford to extract?
That's where the LCOE comes in. They calculated the LCOE for EGS at different depths and different temperatures, taking into account all the costs involved. And then they looked for the lowest LCOE, the most cost-effective scenarios.
So finding that sweet spot where it's both technically feasible and economically viable.
Exactly. And they found that a significant amount of EGS capacity, something like 4,600 GW, could be developed at a cost of 50 euros per megawatt hour or less.
That's pretty competitive, isn't it? I mean, compared to other renewable energy sources.
Yeah, it's right in the ballpark. And they projected that the overall global optimal economic potential could reach 108 terawatts by 2050.
Wow, 108 terawatts. That's mind-boggling.
It is. And that's largely due to the expected decrease in costs as the technology matures and becomes more widespread.
Right, economies of scale. The more we do it, the cheaper it gets.
Exactly. They also provided estimates for individual countries, some of which have particularly high potential, like Russia, China, Brazil, and the U.S.
So lots of opportunity around the world. Now, let's circle back to sustainability. How did this study define and measure the sustainable potential of EGS?
Sustainable potential, as they define it, is all about the long-term picture.
Mm.
It's the rate at which we can extract heat without depleting the resource over time.
Right, so we're not just sucking all the heat out of the earth and leaving it cold.
Exactly. They took into account things like the natural heat flow from the Earth's interior and the heat generated by radioactive decay. They also considered the availability of land suitable for EGS development.
Okay, so it's a more holistic approach, considering the Earth's natural heat replenishment rate. And what was their estimate for the global sustainable potential?
They estimated that we could sustainably generate 256 GW of electricity from EGS by 2050.
All right, so still a substantial amount of energy, but significantly less than the technical potential.
Right, sustainable potential is always going to be lower because it takes into account that long-term perspective.
Makes sense. Now, I know this study also touched on using EGS for combined heat and power, right?
Yeah, they briefly mentioned that. It's basically using the heat from EGS for both electricity generation and direct heating applications.
So like heating buildings and stuff.
Exactly. They cited the Landau plant in Germany as an example of a plant that's already doing this.
Interesting. So lots of different ways to utilize this energy. Now, I want to bring it back to our listeners. We've been throwing around all these numbers and technical terms, but why should anyone care about this? What's the real-world significance of all this EGS potential?
Well, the bottom line is that EGS could be a game changer in terms of our transition to renewable energy. If we can tap into even a fraction of this potential, it could go a long way towards reducing our reliance on fossil fuels.
Right, and we all know how important that is.
And this study suggests that EGS can be economically competitive with other renewable energy sources, which is crucial for widespread adoption.
That's a key point. But I'm guessing there are still some challenges and uncertainty surrounding EGS, right?
Absolutely. One of the biggest challenges is getting accurate data about the subsurface geology. I mean, we're talking about drilling down kilometers into the Earth. It's not easy to know exactly what's down there.
Yeah, that makes sense.
And then there's the issue of induced seismicity, which is basically the potential for triggering small earthquakes when you inject water into the ground.
Oh, right. I've heard about that.
It's a real concern, but researchers are working on ways to monitor and mitigate that risk.
Okay, so it's not a perfect solution, but it definitely has a lot of potential. All right, let's wrap things up. What's the key takeaway from our deep dive into this study? From hot rock to useful energy, a global estimate of enhanced geothermal systems potential.
I think the main takeaway is that EGS represents a massive, largely untapped energy resource. This study makes a very strong case for it as a potential cornerstone of a more sustainable energy future.
And to recap, we're talking about a potential of something like 4,600 GWh of electricity at a competitive cost, with a sustainable potential of 256 GWh by 2050. Those are big numbers.
They are, and I think it really challenges us to think differently about the future of energy.
Exactly. It's not just about solar panels and wind turbines. There's a whole lot of energy under our feet just waiting to be tapped. And this brings us to our final thought for you, our listeners. Given the huge potential of EGS, what do you think are the biggest hurdles we need to overcome to make this technology a reality on a global scale?
We need to consider the economic factors, of course, but also the environmental concerns. It's a complex issue, and we encourage you to dig deeper into this study, from hot rock to useful energy, a global estimate of enhanced geothermal systems potential, to learn more about the potential and the challenges of EGS.
Thanks for joining us on this deep dive. We'll see you next time.